There's one thing I didn't point out here, which I should have. If we look at this pressure time history, in the rapid compression machine, what we do is we do, for each reactive experiment or a reactive experimental point or temperature, we do a non-reactive experiment. So we take a pressure time history for a mixture where we have replaced the oxygen concentration with nitrogen. And that way we have the same, or virtually the same heat capacity, but we have an unreactive charge that's not going to ignite during the time scale. And we can get a wide pressure time history. And then we use that in our reactive simulation to predict or to take account of the pressure time history of the reactive experiment. I hope that's clear. So I didn't point that out when I was going through the lecture. Just for RCM. So I was asked, is it just for RCM or do you do it for shock tube too? So just for RCM because of this heat loss. In the shock tube, we assume that we're at constant pressure. There's a lot of controversy or a lot of discussion whether it's constant pressure or constant volume. But we assume constant volume. Well, actually, sometimes it might be better to take, if you simulate a shock tube experiment assuming constant pressure or assuming constant volume, you get actually a different ignition delay time. They might differ by between 5 and 10%. So it's actually neither. Neither is, it's not ideally either constant volume or constant pressure. So what you could do, but report what you do if you're going to simulate it and write it in your paper. So if you assume constant volume, just say in the simulation you assume constant volume. So somebody can reproduce your data. Maybe the best way to do it would be to simulate assuming constant volume and constant pressure and take the average. Might be the best way. But typically what we do is we say, look, we assume constant volume in the shock tube, and here are our simulation results. That's it. Okay? One last thing, you can see one thing I didn't point out here is even out to virtually 100 milliseconds here, you can see that the temperature that's measured using the laser absorption due to the water matches very well the temperature taking using the technique that I've explained to you. Okay? Okay, so this is showing the shock tube. And we got as far as here, measuring the light. Okay, so if we're just measuring, I'll talk a little bit more about the speciation laser absorption techniques in a minute that's performed by Professor Hansen's group in Stanford, who's been the pioneer in that, really. But here we just show typical pressure time history or light emission time history inside that's measured in a tube. And this is taken from Professor Eric Peterson's group at Texas A&M University for a mixture of propane and air at equivalence ratio of 0.5 at 30 atmospheres and 1,000 Kelvin. And you can see here, here's the shock arrival at the end plate. Here's the rapid rise due to the reflection of the shock wave off the end plate. And here's the pressure time history behind the reflected shock wave then at the end plate. And you can see, I've just put in this horizontal red line, and you can see that the pressure is fairly constant as a function of time until we get ignition. And that ignition coincides, the pressure rise due to ignition coincides quite well with the light emission. And as I said to you before, that for fuel and air, even lean mixtures, it's fairly unambiguous what criterion you use to define ignition delay time. Here, they're pretty much coincident. It might be a little bit more easily defined if you take the light emission. Okay? And that time scale here is, I don't know, 2200, 2300 microseconds, 2.3 milliseconds or so. Okay? So this is a typical pressure or light emission time history that you take assuming that everything's pretty ideal, okay? Or when things are pretty ideal. However, and actually, oh, sorry. So here then, and this would be 1 point. So I don't know, this is the signal in arbitrary units. This is 30 atmospheres reflected shock pressure and 1,000 Kelvin. And so the time here is 2.3 milliseconds. So that's 1 point that we've taken, so for that condition. So then we plot graphs of ignition delay time on the y-axis versus inverse temperature on the x-axis. So this is for a methane, ethane, propane mixture at 5.5 in air at different pressures, sorry. And you can see here at low temperature, the ignition delay times are long, and at high temperature, ignition delay times are short, okay? And here, the open symbols here are data that are taken in the rapid compression machine, and the solid symbols are data taken in the shock tube. And so let's just focus on the 30 atmosphere data, okay? You can see that the times measured in the rapid compression machine, the shock tube, they don't overlap, but they certainly complement one another. And you can see where the shock tube ends, the rapid compression machine starts, and we have pretty good, you can say with some confidence that, okay, these data agree with one another, and it's logical, the extension in temperature, to lower temperature. Now, so typically, if you combine rapid compression machine data then with shock tube data, you get a nice range of temperature from, in this case here, from about 1,500 down to maybe 950 Kelvin or so, okay? Something like that. But it's not really temperature range that, yes, you do get the temperature range, but it's as a result of the time scale that's available to you in the different facilities. So in the shock tube, the time scale goes to about 1-2 milliseconds. And in the rapid compression machine, it ranges from about 5 milliseconds out to maybe 300, okay? Now, the longer the time, the more time you have for heat loss, and that the facility effects to have an effect on your simulation, okay, and make it less homogeneous, all right? But it still allows you to study fuels in those timescales. So I keep coming back to timescale. So you might try and suggest, okay, well, at high temperature, you use the shock tube. At low temperature, we use the rapid compression machine. It's really the time scale in which you use those facilities, okay? But you can see that they're quite complementary. Another thing that I want to show maybe from this graph for future reference is that you can see that at higher temperature, or sorry, higher pressures, the ignition delay times are faster typically than at low pressure. Why? Why is that? Yes, but also, yes, and higher collision rate of molecules is what the student said. But also, yeah, and the concentration of the species is higher. So if we have, well, the density is higher is what you're saying. So we're saying the same thing. Density is higher, then the higher the reactivity. Okay. So both facilities are useful for measuring ignition delay times. They're an important indicator of fuel reactivity. We can measure ignition delay time as a function of temperature, pressure, equivalence ratio, dilution, okay? A rapid compression machine, normally I have temperature range here, but it's actually time scale. But typically we range from 600 to 1100 Kelvin, the shock tube 1100 to 2000 Kelvin. And it's based on the time available to measure the time in the facility. Okay. Now, I focused really on problems with the rapid compression machine and how it isn't, you don't have a homogeneous temperature or pressure history, which results in a homogeneous temperature history. And that's not great if you're thinking about kinetics because of the exponential dependence on temperature, right? But there's also problems with the shock tube too. Okay, and I just want to point that out. And as I said, in Galway, we have both facilities. So it's horses for courses. And you need to be careful looking at the data that you're measuring and what it looks like and whether things make sense or not. So I showed you a little bit earlier that pressure time history. Here's a slide that we published in 2008 in a paper on propane oxidation. Okay? I don't know if it was in color at the time. All right? But here are data taken in our rapid compression machine in Galway. And here are data that were published by Professor Schulz's group in Duisburg in Germany. Okay? And these are same condition, okay, at about 900 Kelvin, maybe 850 Kelvin, so. The ignition delay times measured in our rapid compression machine are 2 orders of magnitude slower, right? 100 times slower than they were measured in the shock tube, all right? Everything else was the same. So I published this paper, or I didn't publish it, I submitted it for review, right? And surprise, surprise, we had 5 reviewers. Normally at that time we might have 3, sometimes 2, right? This time I had 5, right? And most of them said, nice paper, but what do we do with the data? And they didn't really, they said, well, these are some of the first data that were taken in this Galway rapid compression machine, so maybe you're wrong, right? So actually we had also data taken for N-heptane in the same facility, and that data agreed perfectly with data taken at Leeds, in the Leeds rapid compression machine. So unless it was fuel dependent, there was definitely, it definitely seemed to suggest that there was something wrong. Also, as I said, you need to be careful about everything. And this line is the model simulation of the data. Now, as I said, what we do nowadays is we show 2 different lines if we're using a constant volume simulation, which we do for the shock tube, and if we include the facility effect in the RCM. So sometimes if we're showing, we use a solid line for one and a dashed line for the other. Sometimes we flip-flop, but anyway, we use different lines showing that. So here I show it's a solid line, but actually here we're using constant volume in this part of it probably, and here we're using some facility effect inclusion for the simulation, okay? And you can see that the model actually follows, not perfectly, but it follows the RCM data much more closely than it does the shock tube data, right? So it seems to suggest that, and it certainly suggested to me that the RCM data were a lot more correct than the shock tube data. So I based the mechanism for propane on the mechanisms that I had published for N-heptane and isooctane in the late 90s. And I had to do really unscientific, ridiculous rate constant, choose ridiculous rate constant expressions for the chemistry to get the chemistry to match the shock tube data. I didn't to get it to match the rapid compression machine data. I just used normal kinetics for that, which also suggested to me that the RCM data were much closer to the truth than the shock tube data. So we published this, it was accepted, and we said in the conclusions, we didn't know why, and here it was, and that's it, and the reviewer said, okay, and it was published, right? But there was this discrepancy, 2 orders of magnitude. So what's going on? So and here's a simulation of this graph again, and this is just showing then these lines. And really, there's nothing wrong with any of the data, is really what I wanted to say. But how you interpret it is critical, okay? So here now is the solid line assuming constant volume for all of the data. And this is with a more modern mechanism, not the one that we published in 2008, but maybe one that we have in the last couple of years. And here's the simulation then of the rapid compression machine data assuming the heat loss or the volume time histories that we derive from the pressure time histories that we measure experimentally. And you can see actually that when the ignition delay times become short in the rapid compression machine, the prediction of the mechanism is actually faster than even a constant volume simulation. Okay? Now, I don't know whether you quite follow what I'm saying. When we simulate, and pay attention now for a second, when we simulate the rapid compression machine, we simulate from, and we take time zero, not time zero at the end of compression, but time zero when the pistons start to move. So in other words, we simulate all of the compression part, okay? And we allow whatever reactivity that can occur will occur in that compression time, okay? And remember I said in Galway it takes 16 milliseconds, but it's only in the last 3 or 4 milliseconds that we get that rapid rise in pressure or the rapid decrease in volume, okay? Most of the time, there's nothing much happening. But in that last 3 or 4 milliseconds, we do have time for reaction to occur. And when the ignition delay times are short, that reaction in the last 3 or 4 milliseconds during compression is significant, okay? So when we come to predict the ignition delay time, that shortens it, right, relative to a constant volume simulation. So in this blue line simulation, what we're assuming is that nothing has happened when the fuel has reached, or sorry, when the pistons have reached top dead center. And it's only, the reactivity is only starting when it's reached that compressed gas temperature and pressure, okay? And hence, the simulation in this case is longer than it is when we allow for the reactivity that occurs during compression. Okay? I hope that's clear to everybody. Okay? Yes? What do you mean? Here? Well, I think that's pretty good agreement. Yeah, I think it's pretty good agreement. So you were asking about the agreement here. It's pretty good. Anyways, okay, this is the constant volume one, but you cannot assume that the RCM data is a constant volume. It's not. So we have to include the facility effect. And this dashed green line is what we get when we assume that. Yes. So when we include, so I was at, the dashed green line is assuming that we include the volume time history, or the pressure time history, which is converted to a volume time history, okay? So this is assuming constant volume, okay? And so you can see just in this part. Now, in this part, so from here on, you can see that because of the time, remember this is 100 milliseconds, 200, 300 milliseconds time scale. There's a lot of heat loss that can occur, a lot of pressure drop at the end of compression. And hence, the temperature is not the temperature we think it is. Strictly speaking, so really when we plot one of these points, you have to be very careful what you're looking at, right? Certainly, okay, here at 900 Kelvin, and this is something I want to point out and highlight. So here at 950 Kelvin, 900 Kelvin, and so on, the time scale is maybe of the order of 5, 10 milliseconds on this graph, okay? And in that time scale, very little pressure drop will have occurred. So it will be very similar in reactivity to a constant volume case. So when the rapid compression machine and the shock tube data meet, they are coincident, typically. Because at the time scale for the rapid compression machine data, there's very little time opportunity for heat loss, okay, for that lost to the walls and so on. But as the time gets longer and longer, there's more and more time for heat loss. So the facility effect sort of expands the decrease in reactivity and maybe stretches the NTC or the shape of the curve that you see. And unfortunately, there's nothing we can do about it. We have to plot something. You know, we have to fix a point some way. And it's a way of doing it. Typically, the best thing you could do is float the point someplace, but we can't float it. We have to fix it some way on the graph. And that's what we do. Okay? I hope it's clear. Now, so this green dashed line then is the facility effect. This blue line is the constant volume simulation. Okay? And then this red line, red dashed line, is taking the pressure time history from the shock tube. And it also, with the chemistry, matches the shock tube data. So actually, there was nothing wrong. If I go back, there was nothing wrong with any of the data. The chemistry can match both sets of data from the shock tube and from the rapid compression machine if we take the facility effects into account. So I've spoken already about the rapid compression machine facility effects. What about the shock tube facility effects? What am I talking about? So here you can see, okay, the constant volume case and the facility effect are coincident. But from about 1,000 Kelvin and below, then they're not. So what's happening? Okay, so this was the standard ignition that I showed earlier for this propane air at 5.5 at 1,000 Kelvin and 30 atmospheres. Okay, but when we went back and looked, and this is for methane, ethane, but actually for the propane cases too, and we asked Professor Schultz at Duisburg to look at his data for the propane, and he had very similar profiles to this. So you can see for up to about 6 milliseconds, yes, the pressure is constant at about 20, well, I don't know, what's this? Yeah, 20 atmospheres. But after about 6 milliseconds, the pressure rises rapidly to here. And of course, if the pressure is rising, so too is the temperature. The kinetics is exponentially dependent on temperature, and so it's going to be much more reactive. But we're assuming that the pressure is constant right out to here, and then we're getting ignition. Okay? Not a good assumption for this experiment. It is a good assumption for this one. Okay? So if you take this then pressure time history, again, like you do in the rapid compression machine, and you then simulate the points for propane, you arrive back at the simulation, taking that pressure time history into account. Now, what causes the pressure time history? It's some sort of boundary layer effects, but we don't know. It's unknown yet in the community what causes that. But it is known that typically it happens in this, you know, from about 1,000 Kelvin and below in temperature, the data for certain fuels under certain conditions suffers from this facility effect. What exactly is causing it is not known, right? But again, so what I want to point out, so both these results are wrong, we'd say. They're non-ideal. Right? Not that they're wrong, but they're non-ideal. But if we take these facility effects into account, and then we simulate them, and the models match, the lines match the data, then we have some confidence in the kinetics of the propane mechanism. And you can see that it does. Okay? So we can actually get something about the kinetics if we take the facility effects into account and not ignore them. Okay, so all of these data then were found to suffer from this early pressure rise, and hence the difference in ignition delay time of 2 orders of magnitude. Okay, something similar, but it's not the same, right? And this is in a paper, it was published by Professor Hansen's group in 2009. Okay, and they have these data for hydrogen, oxygen. Okay, So 15% hydrogen in air, 3 to 4 atmospheres, and these are the ignition delay times. And you can see again, here's a model GRI mech. Here's a model from my group. It doesn't matter. It's just, it happens that's what they published. And you can see again, at high temperatures, the models captured the data very well. But once we get below about 1050 Kelvin or approaching 1000 Kelvin and below, the models don't agree with the data very well. Okay? And what they found was when they looked at, so here they have a reactive mixture, this dark solid line, a reactive mixture of 4% hydrogen, 2% oxygen, and argon. The pressure is not constant. It's increasing steadily in time. And there's a constant dP/dt of about 2% per millisecond, right? And here, even for the unreactive mixture, it's doing the exact same thing, right? So this shock tube, under this condition, the pressure is rising at 2% per millisecond. For a lot of fuels, this actually doesn't matter too much. We found it for like larger hydrocarbon fuels, it doesn't make a big difference. No, you have to include it, but it doesn't make it a big difference in our simulated result. But for hydrogen, it makes a big difference because hydrogen is so reactive and sensitive because of the H plus O2 reaction, okay? And what they found was then, so again, using this relationship, which is what we use in the rapid compression machine, okay? And we have this, if you simulate this dP/dt, then I don't know which mechanism they used, it doesn't matter, maybe GRI mech, you actually match the data very well, okay? So again, by taking that dP/dt into account and including it in your simulation, you can match the data. Now, this dP/dt is a facility effect, but it's not the same effect as I showed you for the propane, right? And just be careful that you remember that. Here, if you see for the propane, it did stay constant out to 4 or 5 milliseconds, but then the pressure starts to rise rapidly. I think it is actually chemistry related in addition to, so there's some boundary layers that are triggering some chemistry in the fuel, okay? And it is taking off, but it hasn't ignited completely, and then it ignites, all right? So this is much different. Again, you see here, look, it's constant pressure for quite some time. Here, it isn't constant pressure at all for any period of time. There's a dP/dt of 2% per milliseconds, which is consistent throughout the whole time scale. All right? So it's a little bit different. Okay. Okay, so that's just measuring ignition delay times and how you need to be careful in both facilities. Okay, and one thing that Stanford are really the leaders in are using lasers to do laser absorption measurements. And these are very valuable for validating chemical kinetic mechanisms because it gives you species concentration profiles as a function of time behind the reflected shock wave and gives you another validation target to test your mechanism against. Okay? So OH can be measured at 306.7 nanometers. And basically what you do is you shine a laser through. The absorption is proportional to the concentration of OH that's in the path here, and it's detected on the other side. And you can then measure the concentration of OH in this part of the shock tube. But not only can they do it for OH, but they can do it for many other species like CO2 and water and other species like ethylene. Let's look. Okay. Okay, so CO2 was actually very important because of looking at esters, sorry. So ester fuels have a C double bond O group, And that can generate radicals, which can either lead to the formation of CO or CO2. So measuring the concentration of CO2 in the, I think these are pyrolysis experiments of methyl butanoate, can help validate the mechanism for that fuel. Okay? And this is what they're doing. So they're looking at the absorption coefficient as a function of pressure here. And it changes slightly as a function of pressure. And then they also can correct for background CO2 absorption. So here's the absorption profile, here's the background absorption, and here's the corrected absorption profile then due to CO2. Okay? And then you can get the absorption as a function of time. And you can then, they publish that, and we can use it to validate the mechanism and predict what the mechanism predicts in terms of CO2 profile as a function of time. Okay? And then these are just other CO2 time histories for different esters that they measured. Okay. Also, they can measure fuel concentrations, ethylene concentrations. I won't go into these details, but ethylene, there is some interference from propene and butene and other alkenes, but they're able actually to account for that interference and actually get precise ethylene absorption concentrations. It's in there, you can go into it. But here's a sort of a benchmark publication where this showed species time history measurements for 457 ppm N-dodecane oxygen-argon mixture at this condition. And you can see here, they're showing the fuel concentration decay as a function of time, ethylene concentration, water, OH, and CO2. And all of these profiles are very valuable, as I said, to mechanism validation. Okay, so here's just, Amir Farouk worked with Professor Hansen at Stanford, and he just provided the slide for me. And it just gives you a synopsis here of all the different species that can be measured using the laser absorption technique at the different wavelengths, okay, that they can look for. One other thing that they were actually able to do, not only can you do laser absorption measurements and speciation concentrations versus time, but sometimes you can actually back out precise rate constants. And one of the most important rate constants, we'll be doing that, not today, but tomorrow we'll be starting the small mechanisms, or small mechanism kinetics, is the most important reaction in combustion is H plus O2 giving you O plus OH, okay? And here, they were able to use the laser absorption measurement technique to back out the rate of that reaction by following the concentration of water, okay? And they did a water sensitivity plot at various conditions, and they found that under these conditions that are published here, 2 atmospheres pressure and 1100 and 1500 Kelvin, that the only reaction really that the kinetics was sensitive to, or the water profile was sensitive to, was H plus O2 giving you O plus OH, okay? Using, I don't know which mechanism, maybe GRI mech, okay? So if, with the mechanism then, you predict the absorption profile of water that's measured experimentally as a function of time accurately, you can accurately get a rate constant for H plus O2 giving you O plus OH, because it's only sensitive to that one reaction. Okay? And that's what they did. Yes? For which? Oh, I don't know. So I was asked, how did they estimate the sensitivity coefficient? So normally you would look at some change in the water concentration, the predicted water concentration, and by an increase or a decrease in the rate constant, and they would be probably done relative to one another. So by far, the most important reaction that's increasing or decreasing the water concentration is this reaction, H plus O2 giving you O plus OH. So it's sensitivity to water concentration predicted by the mechanism. Okay. And so you can't see it here, but there's an experiment, there are experimental points underneath these curves, and this solid curve is the best fit rate constant for that reaction H plus O2 plus OH, gives O plus OH. If you increase the rate constant by 10% or decrease it by 10%, then you get these lines. And you can see that that is substantially different from what the best fit is. And so I was at a meeting where Professor Hansen was asked, how well is this rate constant then known within the range of temperature measurement that they measured it in? And he said 5%. Okay? Now, one thing that's relevant to the question that you asked is, and this is something that Hai Wang points out, that 5% uncertainty in the rate constant for H plus O2 gives O plus OH is actually still, it's probably as good as you're going to get. But it's still going to lead to a high uncertainty. And I hope you're not coming away with the wrong, it's a very good measurement, and it's a very good rate constant, right? But it's so, that rate constant, the kinetics of most systems are so sensitive to it that if we could decrease the uncertainty even further, it would be even better, okay? Now, it's unlikely we can, but because all of the kinetics are so sensitive to it, okay? So anyway, here is a plot then that was published in their paper, in this paper, which shows the expression for the rate constant, and it agrees very well with a lot of the data in the literature. Here's actually a rate constant that we were using in the O'Connor mechanism that I referred to earlier. So it was actually too fast. But it's within a factor of 2 at 3,000 Kelvin. So you'd say, well, that's not too bad, a factor of 2. But actually, for this reaction, it is very bad. Because, as I said, even 5 or 10% uncertainty in that rate constant makes a big difference to the prediction of a chemical kinetic mechanism. Because flame speed, ignition delay times, and so on are so sensitive to that one reaction that it's very important that you have an accurate rate constant for it. Okay. So to conclude, in my opinion, right, shock tubes and rapid compression machines are complementary. And that if you have a fuel that has ignition delay times that are of the time scale of 5 to hundreds of milliseconds, then use a rapid compression machine. If you have fuels that have ignition delay times, 1, 2, up in the microsecond time scale, 1, 2 millisecond to the microsecond time scale, use a shock tube. And if you want to study a wide range of condition, use both. That's my recommendation, okay? It's good to understand the kinetics of fuel oxidation. A basic thing you can get with both, great basic measurement or ignition delay times, but you can also get speciation data and sometimes even elementary rate coefficients using both of them, okay? This is probably a good place for me to stop today on the formal lectures. Let's spend the next hour working with therm and just going through a few sample calculations in therm so that you get used to it and see the value of using these group additivity methods, okay? So let's take a break. If you haven't downloaded it already, try and do it now, and we'll start back in about 15 minutes, okay?